Hello viewers, my name is Dr. Rajiv. Welcome to my education channel, YouTube Surgery and Orthopedic Education. Today there is an online lecture on biomaterials and scaffolds used in tissue engineering and regenerative medicine or TERM. In the end, please subscribe to our channel and give us a like if you find the discourse useful. Also, don't forget to press the bell icon below to get my videos regularly. Fully repairing or regenerating damaged tissues or organs and restoring their functions is a dream of human beings. The discipline of tissue engineering and regenerative medicine term is a promising approach to meet these needs. Tissue engineering involves a triad of cells, signals, and scaffolds. A scaffold is an engineered matrix that acts as a template for tissue formation to allow cells to populate, migrate, adhere, and produce new tissue or to replace damaged or diseased tissues. Cell signals are provided chemically by growth factors or physically by a bioreactor. Regenerative medicine combines tissue engineering with cell-based therapy, gene therapy, and immunomodulation to induce tissue or organ regeneration in vivo. During native tissue development, new cells integrate themselves with an extracellular matrix. This matrix or scaffold contains structural proteins and acts as a storehouse for signaling molecules that cells use to communicate and organize themselves into functional complexes or tissues. The main goal of tissue engineering and regenerative medicine is to manufacture a functional three-dimensional cell or biomaterial construct which has a similar function as a living tissue or organ. This construct is used to repair or regenerate injured or diseased tissues or organs. The basic requirement for this construct is that it can support cell growth, transportation of nutrients and waste, and gas exchange. Stem cells work as building blocks in regenerative therapy. Apart from cell sourcing, its organization and microenvironment determine the ultimate success of the engineered tissue. Stem cells are cultured under the standard tissue culture conditions to form cell sheets or small three-dimensional collections of cells known as organoids. But these alone are not able under normal conditions to work like normal cells and tissues. Therefore, supporting materials and molecules are needed to create the proper microenvironment for cell proliferation and differentiation into functional tissue. This is often achieved by suitable scaffolding. A scaffold gives physical support and shape to the engineered tissue, mimicking the native extracellular matrix. This stem cell-seeded scaffold provides a framework for cell attachment, migration, growth, and differentiation and allows cells for reorganization into a functional 3D construct for implantation. These important factors provide sustainability and durability to tissue engineered constructs by facilitating growth, induction, and long-term maturation. Tissue engineering combines cells from the body with highly porous 3D scaffold biomaterials to regenerate damaged tissues. These scaffolds act as templates for tissue regeneration and for guiding the growth of new tissue. Donor stem cells are seeded into these scaffolds to construct or restore a functional tissue or organ that can then be implanted in the recipient. The 3D biomaterial complex or scaffold functions similarly to the in vivo tissue extracellular matrix. The tissue engineering designs scaffolds that are biologically compatible with the area to be regenerated. New cells are then either attracted to or grown directly onto the scaffold. These cell-seeded scaffolds are either cultured in vitro to synthesize tissue constructs which are then implanted into an injured or diseased site, or are implanted directly into these sites using the body's own systems, where regeneration of tissues or organs is induced in vivo. Scaffolds are either natural or artificial. The natural scaffolds are derived from intact human tissue, while artificial ones from engineered implantable biomaterials. Regenerative scaffolds should provide physical support and shape to the engineered tissue as well as guide and promote cell growth, attachment, migration, proliferation, and differentiation. They should enable oxygen, nutrients, and cell signals or growth factors to reach all cells. Scaffolds should also be biocompatible, non-immunogenic, and biodegradable. The selection of scaffolds that best fulfills the requirements for tissue engineering is dictated by the nature of the tissue to be engineered. Ideally, the scaffold must be strong enough to allow surgical handling during implantation. While this is important for all tissues, it is particularly challenging for cardiovascular and orthopedic applications. The architecture of scaffolds is of critical importance. A scaffold should have high porosity and an interconnected pore structure. This porous interconnected structure allows cellular penetration and adequate diffusion of nutrients to cells and the extracellular matrix formed by these cells within the construct. Furthermore, such a structure should allow the diffusion of waste products out of the scaffold without interference with surrounding tissues and other organs. For tissue engineered constructs to become clinically and commercially viable, they should be cost effective. The final criterion for scaffolds in tissue engineering, upon which all the criteria listed above are dependent, is the choice of biomaterial from which the scaffold is fabricated. The choice of material used is again highly dependent on the mechanical and structural requirements of the construct, which differs according to the desired tissue product. Natural scaffolds are derived from human or other animal donor tissues. Here, the native resident cells are chemically removed using a detergent, leaving behind only the extracellular matrix that preserves the original architecture of the tissue or organ onto which new donor cells are seeded. Natural scaffolds come either from a patient or a healthy donor. They have the advantage of retaining the unique structural and functional architecture of complex tissues. They also provide key cell signals that guide the growth and differentiation of the cells used to repopulate the scaffold. Unlike synthetic scaffolds, natural scaffolds are biologically active and promote excellent cell adhesion and growth. They are also biodegradable and so allow host cells with time to produce their own extracellular matrix and replace the degraded scaffold. However, scaffolds made from biological materials generally have poor mechanical properties which limits their use, for example, in load-bearing orthopedic applications. Typically, natural scaffolds are obtained by the decellularization of biological tissues either by dipping tissues in agent or perfusing them with a detergent via the arterial tree. This removes most or all of the cellular elements from the tissue or organ but leaves the collagen-rich extracellular matrix and intricate anatomical structures almost intact. The decellularized natural matrices serve as a versatile scaffold compatible with the stem cell proliferation and specialization. Decellularized natural scaffolds are not susceptible to immunological rejection because these are seeded with autologous cells derived from the potential recipient to create an organ. Hence, there is no need for immunosuppressive drugs and no risk of their attendant side effects. The use of natural scaffolds is particularly suited where the donor tissue is relatively easy to obtain, for example, trachea. The natural scaffolds are specially suited to engineer whole organs such as the kidney or liver. The main advantage here is that the extremely intricate three-dimensional structure of the organ is preserved, which would be extremely difficult to achieve using engineered artificial materials. However, a significant disadvantage of using decellularized scaffolds is that it needs a whole human organ to make each organ, and the availability of such organs is limited. Scientists are continually developing new materials to create artificial scaffolds. These scaffolds also should be biocompatible, biodegradable, and bioreabsorbable. Artificial scaffolds are made from both natural and synthetic materials. Typically, three different groups of biomaterials are used in the fabrication of artificial scaffolds for tissue engineering. These are natural polymers, synthetic materials, and ceramics. Natural polymers used include collagen, polysaccharides, fibrin, gelatin, and cellulose, while synthetic materials include various synthetic polymers such as polylactide, polyglycolide, and carbon compound graphene. Bioactive ceramics or bioceramics and bioactive glasses or bioglasses are widely used for skeletal tissue repair. Hydroxyapatite or tricalcium phosphate is an example of bioceramic. Ceramics are known to enhance osteoblast differentiation and proliferation. New bioactive glasses are based on borate and borosilicate compounds. They are biocompatible and enhance new bone formation. Artificial scaffolds are commonly made from synthetic biodegradable polymers. They can be produced with reproducible physical characteristics. Artificial scaffolds can also be fabricated using a combination of natural and synthetic components to optimize their performance. Most artificial scaffolds are fabricated as a porous three-dimensional structure and in many designs using 3D bioprinting technology. A great limitation of traditional artificial scaffolds is that they do not support vascular ingrowth to restore the vascular integrity of the transplanted tissue or organ. Hydrogel scaffolds are a new area of research in the field of tissue engineering. These are composed of cross-linked hydrophilic polymers that can absorb very large amounts of water while maintaining their three-dimensional shape and structural integrity. These scaffolds can repair or regrow damaged biological tissue and are highly beneficial for the treatment of injury and disease. Hydrogel scaffolds are fabricated from naturally occurring polymers such as collagen and fibrin or artificial cross-linked polymers such as egg polylactide. They can be impregnated with growth factors to promote cellularization, proliferation, migration, and differentiation. They also permit oxygen and nutrient transport and mimic native soft tissue. The limitation of vascular regrowth in traditional artificial scaffolds is being tried to overcome using the 3D bioprinting technique. This technology allows the production of scaffolds that have pore size and diffusion characteristics needed to provide the necessary cellular signals for cell differentiation, proliferation, migration, and differentiation. Artificial scaffolds now can be engineered to allow the incorporation and retention of particular cell growth factors, including angiogenic growth factors such as vascular endothelial growth factor, to stimulate the growth of a vascularized functional tissue construct. Electrospinning technology is being used to produce scaffolds composed of nano-sized fibers. One of the main advantages of the electrospinning technique over other fabrication methods is the creation of scaffolds with multiple arrangements and morphological structures, such as tubular scaffolds, flat surfaces, and asymmetrical configurations. Microsphere-based scaffolds are a type of artificial scaffold composed of flowing microparticles known as microspheres. Microspheres provide a structure for cells to reside in, which is important for tissue regeneration. These scaffolds have been used in various applications, including bone regenerative applications and for constructing drug release scaffolds. Recent developments in material science have led to the creation of so-called smart scaffolds. They are complex and innovative artificial scaffolds combining ceramics with polymers to gain the advantages of each. They have biomimetic properties and provide biophysical cues or cellular signals to instruct, guide, and modify cell behavior. Smart scaffolds can respond to environmental stimuli, mimic the dynamic nature of the native extracellular matrix, and are thermoresponsive and hydroresponsive. Smart scaffolds have been mostly used for regenerating bone, cartilage, and cardiovascular tissues.